Welcome back to AP Stat. We're in Chapter 2 where we talk about displaying and describing categorical data. If you are familiar with this vessel, you know that it was ill-fated. This is the Titanic. In addition to supplying a very sad story for history and for supplying the plot to one of the most famous movies of the late 20th century, it also gives us a lot of material for a statistics class. We're going to be exploring the Titanic throughout this section. All right, categorical versus quantitative data. Well, we talked about categorical versus quantitative variables. Now we're going to look at data that fit those categories and how they look in a graph. On the left, we see categorical data, and that concerns counts, percentages, etc. of a qualitative variable, all right? So on the x-axis, we have pepperoni, sausage, cheese, and supreme. I assume pizzas, calzones, what have you. The quantity, the count, is on the left-hand side over here. So obviously pepperoni has the highest count, then cheese, then sausage, and then supreme in terms of your flavor of pizza or calzone or what have you. You have this categorical variable over here, this variable of type of pizza or calzone or stromboli or whatever. All right, let's talk about this graph over here. Fundamentally different. These are quantitative data, and that concerns counts, percentages, etc. of a quantitative variable. So we have incomes here in 2008. Not a great year for a lot of people's incomes, but here we go. We have a US dollar that is obviously a quantitative variable. It is not only a number, but it has meaningful units. And so we have a quantitative variable. These are individual incomes, anywhere from you're making a good chunk of change all the way down to you have a part-time job during the summer or something like that. So we have millions of individuals. We have a little over 20 million in this category over here. We have between 10 and 15 million in this category over here. So we have the count on the left-hand side and the number of and the amount of money on the x-axis. And we see how many people fit this income, this income, this income, and so on and so forth. So that's how graphs look dealing with categorical versus quantitative data. Now we're going to talk about some tables. A lot of this section deals with tables. These are frequency, that's the one on the left, and relative frequency, the one on the right. Okay, so let's talk about this table on the left. This is a frequency table. All right, what is frequency? Well, it's the number of times a particular value for a variable has been observed to occur. So we're talking about the Titanic, warned you about that. We have first class, that many, second class, that many, third class, that many, and crew, that many. Basically fourth class, and we'll find it is below third class later on in this section. Things did not go well for the crew of the Titanic, to say the least. Over here, we have a relative frequency table for the same set of data. Now, what's relative frequency? Relative frequency is the proportion of times a particular value for a variable has been observed to occur. Here's the relative part, relative to other values of that variable. So now we don't have counts anymore. We actually have percents. And so we have first, what percent of the whole fit the first class, what percent of the whole was in the second class, third, and what proportion of the crew aboard the Titanic were the crew. A couple notes here. Each calculation is made by dividing the part by the whole. So how did we get this 14.77 number? Well, we took 325 and divided it by the total number of people aboard the Titanic, which happens to be 2,201. No, I did not just do that in my head. You do statistics for a little while and you have in the back of your mind that there were 2,201 people aboard the Titanic. It just comes with the territory. So I've memorized that number. We take 325 first class folks, divide by 2,201, and you have about 14.77%. For second class, you take 285 divided by 2,201, and you get 12.95%, so on and so forth. All right, in a relative frequency table, the percentages should sum to 100%. Now, there is a chance that they don't. A prime example here is this very table. The percentages, if you added them all together, I believe would be 99.99%. And that's because of rounding, okay? We have in our hundredths place a 7, a 5, an 8, and a 1. Actually, it might be 100.1%. I don't know. But it should be very close to 100%. Should be very close to 100%. All right. This table here, the percentages are not exactly at 100%. That's okay. They should just be very, very close. All right. Bar charts. So we have the bar chart for the frequency and relative frequency, and it should not surprise us that the bars look about the same between the frequency and the relative frequency. Bar charts are appropriate for categorical data, all right? In these bar charts, there is some nice separation between the bars, which tells us intuitively that we're dealing with different categories. Those categories we call classes. First, second, third, and crew are all classes, each of which get their own little bar. These charts are examples of a good application of what is called the area principle. That principle says the area occupied by part of a graph should correspond to the magnitude of the value it represents. In English, that just means that the bigger the bar, the bigger the value associated with that class. All right, so obviously there are more crew members than first class, so we'd expect the bar to be bigger for crew than first. But we expect the crew to be bigger than third by not as much, all right? So the size of the bar should correspond to the magnitude of the value it represents. That kind of seems like a well-duh sort of principle, but you would be surprised by how this principle is routinely and sometimes strategically abused in the way that people present statistics. Now let's talk about pie charts. Data that are supposed to show a part-to-whole relationship. There we go. I promised you. Data is a plural word, but I used a singular verb here. Oops. They should say are. Best displayed with a pie chart. All right? Do as I say, not as I do. Data is a plural word. That should say are. All right? So data that are supposed to show a part-to-whole relationship are best displayed with a pie chart. Okay, so we have these grades here and something familiar to all of you, raising money for your senior trip. And then we have a percent of the total. If I were to go into some way of making a pie chart and create this pie chart here, you'd get to see the part-to-whole analysis. There's a small slice of the pie devoted to freshman year, little larger, and then by the time we're a senior, we got to be making a whole lot of money for our senior trip. All right, so part-to-whole analysis is something that we need to have when dealing with a pie chart. You can't just use a pie chart for any categorical data. And we'll talk about why this graph is a bad example of a pie chart in just a moment. The categorical data condition is a term that our textbook uses to say that data need to be counts or percentages of individuals in non-overlapping categories in order to use the pie chart or some graph that's like it. Okay, so in order to use a pie chart like this poor example of a pie chart or this improved example of a pie chart, we need to follow the categorical data condition. Our data need to fit that, okay? Bar charts can be used for data sets that break the categorical data condition. You can have a bar chart that displays data relating to categories that overlap, like what we have going on here. What we have is a political analysis of the 2012 election. You have Sarah Palin, Mitt Romney, and Mike Huckabee. You can, in theory, back more than one candidate. You could, in theory, back Huckabee and Palin. You could, in theory, back Palin and Romney. You could, in theory, back Romney and Huckabee, all three, only one, or none of the above. But a pie chart is not good for this scenario because it adds up to more than 100%, and the idea of part-to-whole analysis is ruined because apparently the whole is 193% or something like that, which the whole should add up to 100%, not something bigger than 100%. So how can I tell the categories depicted in the graph to the right that is now infamous on the internet don't follow the categorical data condition? Well, the percents add up to more than 100%. The categories must be overlapping. There must be people who are backing more than one candidate or all three, all right? There's no other way the data could turn out like this. There's no reason to think the data are wrong, all right? Very probably rounded to the nearest whole number percent, but there's no evidence to say that opinion's dynamic is wrong or that anyone displaying these data are wrong. It's just a poor choice of how to present the data. All right, more on appropriate representations of data, staying in the world of politics. Recently, a Gallup poll, now recently as of like 2018, I bet opinions have changed on this, probably for the worse. Recently, a Gallup poll asked 824 people how they viewed a variety of professions. All right, Gallup and Pew being among the two most important survey groups out there. If you see a Pew Research poll or a Gallup poll, that is the gold standard for good research or good sampling, good practice of statistics. All right. So, a Gallup poll asked 824 people how they viewed a variety of professions. Specifically, pollsters asked, how would you rate the honesty and ethical standards of people in these different fields? Here are the results from members of Congress. The results were as follows. Some people think very highly of Congress. Some people don't want to express their opinion. A lot of folks think that the folks in Congress are a little bit sketchy. All right? Such is politics. Right. What kind of table is this? All right. Is this a frequency or relative frequency? Well, what should cue you to the correct answer is our column to the right. Percent. If you see percent, that refers to relative frequency. Part to whole analysis. Okay. So we have part to whole analysis here. Which of these, the bar chart or the pie chart, would be appropriate for the data? All right. Part to whole analysis, these are non-overlapping categories. You can't choose both very high and average and low all at the same time. These groups are distinct. These percentages add up to 100%. So I think the pie chart would be the best way of displaying. However, you could use the bar chart. But that part to whole analysis, I think, lends itself more to the pie chart. Not that the bar chart is illegal, just that the pie chart does a little better at explaining what the data are saying. All right, more inappropriate representations of data. Pew Research Organization asked 1,005 U.S. adults which of the following electronic items they use: cell phone, smartphone, computer, handheld e-book reader, Kindle, Nook, that kind of stuff that maybe some folks who are a little older than you use. Or you may use them too, no offense. Or just a tablet. Okay. The results were as follows. All right, you take one gander at those percentages. You take one gander at the top two percentages, and you realize that this is not a good part to whole analysis. The categories must overlap, which makes sense. I mean, You have a dumb phone and a smartphone. Okay, fine. You probably don't have both of those at once. But I'm pretty sure all of you have a smartphone and a computer, or a smartphone and a tablet. I feel like most elementary schoolers these days have a smartphone and a tablet at the same time. So it's not an exaggeration to say that these categories are almost certainly supposed to overlap, all right? And the data clearly say that they do, all right? Is this a frequency table, relative frequency table, or neither? This is a relative frequency table. This percent thing is a cue that we are dealing with. Oh, hold on. Got to think about this a little more if you came to that conclusion. This is not a relative frequency table because this is not a part to whole, all right? Since we don't have a sum to 100%, we should not conclude that this is a relative frequency table. It's actually neither, right? Clearly it's not a frequency table. If it were a relative frequency table, these fellas would have to add up to 100%, and they do not, all right? How could we display these data? Bar chart or pie chart or both? Well, this is not a part-to-whole analysis, okay? We have overlapping categories, so pie chart is right out. We cannot use it. So the only way to present these data would be a bar chart, something like this. This chart does allow the data to speak, all right? We can tell that the highest proportion of people use cell phones as opposed to any other technology. But still, it's very clear looking at that y-axis. This cannot possibly be a part-to-whole analysis. Okay, so we can learn a couple things immediately just by looking at the graph. These bars do allow the data to speak quickly and efficiently. Since the data don't abide by the categorical data condition, namely the data counts are percentages of individuals in non-overlapping categories, only a bar chart would be appropriate. All right. Let's talk about the value of displaying data through pictures and, for some, the value of using pictures to distort what data are saying, okay? Which representation of the data gives us a fuller understanding of what it's saying and is frankly more appealing? You look at this on the left here, okay? We have names of teachers, I'm sure you know. These data are outdated, by the way. You can look at this name right here. She hasn't been called that in a couple years. That's Mrs. Smith. And so these data are clearly outdated, all right? But you have these numbers associated with them, and they're kind of in a random order. Okay, now we look at this part-to-whole analysis right here displayed in this pie chart, and first off, it's more visually appealing. You have colors, you have shapes, you have clear indications of the names popping out of the pieces of the pie chart. I would go with this one right here as the more appealing way of displaying the data, and it also gives us an understanding of what the data are saying. This is a representation of all of the classes at FCA. And each part gives us an idea of, okay, I have 5 classes, but what part of the whole number of classes offered in the math department was I teaching, all right? This representation helped the data to speak. It's truer to the mission of the data, which is to talk about how the math classes are divided among the teachers, okay? So we can see that this graphical representation is very nice and very useful, and this over here is kind of helpful, but frankly boring. Displaying data with pictures helps show trends or relationships that may be hiding in your data. If we just have a bunch of numbers over here, is it possible to compare the values one to another? Well, sure, but this doesn't tell you how my 5 classes fits in with the whole very well. Now we can see the proportion my 5 classes fits in with the whole. We can also make outliers more obvious. The most obvious thing that I see in this chart in regards to outliers is that there are none. We don't have one math teacher teaching 10 classes. That slice of the pie would be a very large slice indeed. So, looking at this, I can tell there are really no outliers. And explain what our data are. Again, there it is. What our data should be are saying to others. Okay? So, again, it's a part-to-whole analysis. How is the math department divided up? This is an easy way of explaining how it's divided up to someone who doesn't want to look at a boring table like this. Now we're going to talk about the misuse of graphs, ignoring the area principle. Every election, if you're on social media, you're going to see a graph that looks something like this. And it's going to be usually from someone who is, I'm not making a political stance right here, of course, just saying what I usually see on social media. That someone of a conservative bent is saying, look how much of the country is red. Okay, so obviously the Republican Party should be winning this one. All right. Well, what you will often hear as a retort is land can't vote. All right. And what that's saying is that we have a violation of the area principle on our hands. The area principle says that the area occupied by part of the graph should correspond to the magnitude of the value it represents. Okay? So if we're talking about voters, yeah, sure, Wyoming is a big place. It's a big box in the middle of the western United States. But Wyoming is not heavily populated. So we should be talking about Wyoming in terms of the size of its population, not in terms of the size of its land. So a better way of representing the 2012 Electoral College map is to look at a graph like this. Of course, it looks a little wonky. This looks nothing like a graph you've ever seen. Alaska looks even more like a little island in the Pacific, as some uneducated folks may assume it is, always seeing it in a corner here. I actually ran into someone who thought that Alaska was a little island in the Pacific. Oh no. Anyway, this graph looks really silly, okay? But all the same, you have an electoral map that follows the area principle. The size of each state corresponds to the size of the population of the state. All right, we have Wyoming over here being wee tiny and very large relative to states in the Northeast. And then you have Wyoming here being dwarfed by little states such as Connecticut, and even Rhode Island is a little bigger than Wyoming over here. So this gives you a much better idea of why Obama won that election over Mitt Romney. All right, the numbers here agree much more with the electoral map. All right, another common misuse of graphs is restricting the vertical axis. This is a classic example. If you go on the internet for bad graphs, this is going to be at the very beginning of the images that you would see. All right, we got Danielle, Jared, and Alexi, and they have computation scores. All right. Apparently they took some kind of test, and Danielle scored like 3 times better than everyone else, except no. Everyone else was scoring somewhere around a 96. Danielle was scoring somewhere around a 97. This is a deceptive graph. Is it mathematically incorrect? No. Danielle could have gotten 97, and Jared and Alexi could have gotten 96. Here's the problem. Look at that y-axis. It only contains a range of 1.5. All right, the difference between the highest value and the lowest value is 1.5. Okay, that is not a good graph if these are test scores. All right, and that may be mathematically accurate, But if you were to have a y-axis go from whatever the failing grade is, say 59.5, all the way up to 100%, these bars would be at exactly the same height pretty much, with a very minor difference, of course. And we would say, oh, Danielle, Jared, and Alexi all did about the same on the test, okay? That would be an honest graph. Here's another one you'll see very early on if you were to search bad graphs. Massive increase in home price. Oh, wow, your home tripled in value. Actually, no, it didn't. It went from 80,000 to 82,000 euro, all right? That's not a huge increase, all right? Going up 2,000 euro, that's not a huge increase, all right? So this is a deceptive graph. You want to be looking out for those deceptive graphs, okay? Now, one big important note here. Sometimes it is important to restrict the y-axis if small changes make for big results. Human body temperature, for example. You wouldn't want the y-axis starting at 0, okay? And going to, I don't know, 110, all right? Yeah, a small change in human body temperature means that anywhere from you have hypothermia to you could be in the hospital with a fever above 103 or something like that. Small changes in body temperature make for a huge difference, all right? So if that is the case, which is not the case in either of these graphs, you're definitely going to want to restrict that y-axis. If you're talking about human body temperature, probably want to go between 95 and I don't know, like 103, 104 if for your y-axis. Values beyond that are pretty much useless. Okay, but in general, if you see a really restricted y-axis, that should raise an eyebrow. You're probably looking at a graph that's made for the express purpose of deceiving you.